Hi, welcome to lesson 8.2, proving triangle similarity by angle. So before we get started, let's go ahead and get our papers ready for the lesson. Now, on page 226, we are not really going to do the whole table. We are simply going to look at only a few aspects of the table because I think it's kind of redundant to do the whole table. So we are going to not do these columns right here because I think we can get the idea basically with the first column only. So on page 226, please make sure you cross out basically all of this. Now we're still going to need some of the space around here, so make sure you guys keep that clear. On page 227, you are going to need a blank piece of paper, and this is going to be for example number 3. So pause the video, get yourself a paper, glue it on, and that is for problem number 3. Turn to the next page, page 228, and we are going to do example number 1 here and example number 2 right there. We'll come back to this theorem in just a second. Once you're done with that, please go back to page 226. Okay, so we are exploring today a concept called similarity. So what exactly is similarity? We learned that in chapters 4, when we did dilations, that when you apply a scale factor to a certain polygon, it grows or it shrinks evenly. We call that an enlargement or reduction. Now the angles pretty much stayed the same. But now we're faced with a scenario where we have a set of triangles that have two angles that happen to be congruent. So the question is, what is going to happen with this right here and this right here? Okay, so let's take a look at the triangle angle sum theorem. Okay, and let's look at what kind of angles are we going to get from here and here. So basically, I need to do 180, take away the sum of 106 plus 31. Okay, so that's 180. Take away 137, okay, which I know that is going to be 43 degrees. So this is going to be 43 degrees. Now, both of these are going to be 43 degrees. So as you can see, you have 1, 2, 3 pairs of angles that happen to be congruent. Now, we don't have the actual measurements from here because they come from a geometry software. So there is a, the measurements are pretty much included there. So I'm going to show you guys what those are in just a second. So these are the corresponding lengths. Now remember, this comes from the geometry software that comes with our curriculum. So these are the actual measurements that you can see right there. Okay, so you can actually copy them right onto it if you want. This right here is 4. This right here is 3.04. This right here is 565. This one here is 6.97. And this right here is 9.84. And this is 5.3. So if this is too small, here is the measurements. Go ahead and pause the video, write down the measurements. And then once you're done, continue with the video. So now what we're going to do is we're going to use those same measurements to come up with a couple of ratios. And we're going to see if we find anything interesting. So first off, let's go ahead and write down these. AB is 4. Okay, DE is 6.97. BC is 5.65, EF is 9.84, AC is 3.04, and DF is about 5.3. So what exactly are we going to do with these numbers? Okay, we're going to look pretty much just look for the scale factor and see if we're going to get the same thing. Okay, so let's see how this is going to look like. We're going to compare DE to AB. So we're going to look at 3 different ratios. Okay, So let's see. First ratio we're going to look at, and I don't have a lot of space here, is the ratio, let me lift it up a little bit, DE to AB, okay? The ratio of EF over BC, because we have DE over AB, EF over BC. And the third ratio is going to be DF over AC. DF over AC, because those are the corresponding sides. Not that they're congruent, but they're corresponding. So let's look at the measurements right there. So DE is 6.97, AB is 4, EF is 9.84, and BC is 5.65, and DF is 5.3, and AC is 3.04. So what exactly am I going to do with these numbers? Well, I'm going to divide them. So I got my little calculator here handy. I know you can't see the whole thing on the screen, but 6.97, oh, I have an email, divided by 4, that's about 1.74. Okay, so I'm rounding to the nearest 100. 9.84, divide that by 5.65. It's going to be about 1.74. And then the last one, 5.3, oops, divided by 3.04, gives me about 1.74. So as you can see, our scale factor is the same for all of these, which means that they are going to be similar. So all it took was 2 pairs of angles congruent in order for these 2 triangles to be considered similar, which brings us to our next theorem, which is the angle similarity theorem. Okay, so let's take a look at that. Let's go to page 228 and let's talk about it. Okay, the angle similarity theorem states that if 2 angles of one triangle are congruent to 2 angles of another triangle, then the 2 triangles are similar. And since we can show that they're similar, their sides are going to be proportional. Therefore, we can use it in applications to find missing lengths. So let's go ahead and begin our examples. Remember, example 1 goes here, example 2 goes here, and example 3 goes in the previous page on page 227. So let's begin with our first example. All right, so let's take a look at example number 1. It says determine whether the triangles are similar, and if they are, write a similarity statement explaining your reasoning. So remember, we are looking for applying the angle similarity theorem. So what do we need to look for? 2 pairs of congruent angles. From what we can see in this diagram, we have a set of right angles, which we know that all right angles are congruent. So here is my first pair of angles. I need a second pair. This one's 26, this one's 64. So far, I don't have anything. Now, we do know that we can figure out what one of these angles is going to be. So what we're going to do is we are going to, we know that this angle and this angle are going to be complementary. So whatever 90 minus 64 is going to be, it's going to be the measurement of that angle right there. 90 minus 64 is going to be 26. So this angle right there happens to be 26 degrees. So now that we can see that this is 26 degrees and this is already 26 degrees, we now have our second pair, which means that these triangles are going to be similar. Now, which one's the pre-image, which one's the image? If it doesn't tell you, it doesn't really matter what order you put it. But let's go ahead and write a similarity statement. So let's start off with a triangle on the left-hand side. Triangle CDE. Now, similarity statement, all it is that. Okay, CDE similar to, now C is going to correspond to K, D corresponds to G, and E corresponds to H. Hence now, this is my similarity statement. Okay, and these two are similar because of the angle-angle similarity theorem. And what were those two angles? Angles D and G and angles C and K. Do we really need this one? Well, we could have done it the other way too. I could have found this one and found it congruent to this one. So the simple fact that you have two pairs of angles congruent allows you to say that these two are similar. Let's look at example number 3. Okay, for example number 3, it says, show that the two triangles are similar. So we have triangle ABE and triangle ACD. Based on what we see here, we only have one pair of angles congruent, but there's one thing that we are not paying close attention to, is the fact that this angle right here is a common shared angle between this triangle right there and the outer triangle. So they both have technically two pairs of angles congruent. Okay, so therefore this and this is going to be similar. So show that the two triangles are similar. So how do we write it? Well, we can say this. We can say that angle A is congruent to angle A. Okay, and we can say that angle ABE is congruent to angle ACD. Yes, you can say that. This is also the reflexive property of angle congruence, which is going to be very useful in the next couple of chapters. All right, let's take a look at B now. So right off the bat, I can already see that we have the intersection of two lines. So I already know I have this angle right here congruent to that angle. That's my first pair. Now, my second pair can come from many different directions. It can come from the fact that these two lines are parallel, and I have these two angles and these two angles. So there's technically 3 different ways to explain this problem. Without even using this, I could not use this and still got the other two. So I am just going to use this one and this one. We deducted that. It wasn't given to us, but we deducted. So we know that angle R is congruent to angle T. And what was the reason? The alternate interior angle theorem. So that's one pair. Okay, I probably should number these. 1, 2. Here's my first one. My second one, I could either do the same reason for these two S and U or my vertical angles. Okay, so you got choices. So I'm just going to use angle S, V, R congruent to angle U, V, T. What's the reason? Vertical angles theorem. All right, so those were easy. Let's take a look at example number 3 and pretty much our last problem. Hope you guys can hear me well. I have the AC on and it's a little noisy. Okay, a flagpole casts a shadow that is 50 feet long. Okay, so I know it's a little hard to see here, but what you really have here is a flagpole creating a shadow of 50 feet long. Okay, at the same time, a woman, I'm going to probably get a little more space here, is standing and her height, this height, happens to be 5 feet 4 inches. Okay, and she is casting a shadow that is 40 inches long. And they want to know, how tall is the flagpole going to be? Okay, now here's the thing. I know you don't see it, but there is a sun. Yes, my son has a smiley face. How about that? Okay, so the sun is casting a shadow, okay, and it's actually creating a set of congruent right triangles. Not congruent right triangles, similar right triangles. Okay, where this angle being casted is pretty much the same thing as this one. So these two happen to be similar. And I want to know what is going to be the length of the flagpole. Okay, so I'm going to go ahead and set up my ratio. Okay, but you notice I got a little bit of a problem here because I have feet and inches, I have inches, and I have feet. Is that going to really matter? I honestly think it is going to matter. We need to convert everything into inches just to make things a little bit more simple. Now, we do know that 1 foot is equal to 12 inches. Okay, so if I convert these 5 feet into inches, that's going to be 5 times 12, which is going to be 60 feet plus another, 60 feet, I'm sorry, 60 inches plus another 4 inches. That's a little sloppy. 60 inches plus 4 inches, that's going to give me 64 inches. And my 50 feet, I can convert those also and give me 600 inches. All right, so we're going to set up a ratio. Okay, so the ratio is going to go like this. Now, because these two are similar, they're going to have the same scale factor. They should reduce to the same thing pretty much. Okay, so 64 is going to correspond to x, and 40 inches is going to correspond to the 600 inches. So I'm going to set up my ratio over here. 64 inches is to x as 40 inches is to 600 inches. Now, you realize that that's gone and that's gone. Okay, so now our goal is to solve for x. So we can also get rid of one of these zeros. We can do that. Cross multiply, that gives me 4x equals 60 times 64 inches. Now, let me type that in. That's going to give me a total of 3,840 inches, which I'm going to divide it by 4, and that is going to be 960 inches, but they want the answer in feet. So what do I need to do to these 960 inches? I need to divide these by 12 in order to convert that into feet, because we know that 1 foot equals 12 inches. Okay, so when I divide that by 12 inches, I get my units of feet. So 960 divided by 12 is going to give me a total of 80 feet. So the flagpole is 80 feet tall. Once again, thank you for watching, and make sure you guys complete all of your extra practice.